All right, welcome to the Explainer. Today we're going to pull back the curtain on a really cool problem-solving tool from the world of AI. It's a way of thinking, really, that helps computers tackle everything from a simple Sudoku puzzle all the way up to crazy complex logistics problems. And it all boils down to one simple question.
So, let me ask you this. How would you even begin to solve a puzzle that's just packed with rules? Think about a Sudoku grid or something similar. It's all about making sure every piece fits following all the rules, right? So how does a computer do it? I'll tell you, it's not just by trying every single option. That would take forever. No, there's a much smarter way to go about it.
Okay, so to really get a feel for this approach, let's start with a classic challenge. It looks pretty simple at first glance, but trust me, it shows off the core idea perfectly.
Okay, so picture this. You've got a map of Australia in front of you and a handful of colored pencils. Simple enough, right? Just color it in. But wait, there's one really important rule. No two regions that touch each other can have the same color. So for instance, Western Australia and the Northern Territory, they have to be different colors. Same goes for any other neighbors.
All right, so let's get specific about our little puzzle here. We've got 7 regions to color. We've only got 3 colors to work with: red, green, and blue. And the big rule, the one we can't break, is that neighbors have to be different colors. So those are the basic pieces we have to play with.
Now here's what's so cool about this little map puzzle. It's actually a textbook example of a much bigger concept in AI. Researchers call it a constraint satisfaction problem, or CSP for short. Think of it like a universal blueprint for setting up problems based on their rules. And when you frame a problem this way, well, it suddenly becomes way easier for a computer to figure out.
And it turns out that pretty much any problem you can describe as a CSP is built from the same 3 core ingredients. It's kind of like a recipe, right? If you can just figure out what these 3 things are for your specific problem, you've basically translated it into a language a computer can work with and solve really fast.
Okay, first ingredient, variables. These are just the things you need to make decisions about, the unknowns you're trying to solve for. So, in our Australia map puzzle, the variables are the regions. Simple as that. We need to pick a color for WA, a color for NT, and so on for every single region.
All right, next up. Every one of those variables has a domain, and the domain is just the list of all the possible options for that variable. So, for our map puzzle, the domain for every single region is exactly the same. It's that little set of colors we have: red, green, and blue.
And the third, and honestly the most important ingredient, the constraints. These are the rules of the game. They're what tell you which combinations are okay and which ones are totally forbidden. So for our map, the big constraint is that the color you pick for Western Australia cannot be the same as the color for the Northern Territory. And that exact same rule applies to any 2 regions that share a border.
Okay, so now that we have the framework, let's see how it works on something other than maps. You've probably run into these kinds of problems before and just didn't know they had a name. This is where things get really interesting, where you see how powerful this way of thinking is.
So let's compare map coloring with, say, Sudoku. I mean, they look totally different, right? One is colors on a map, the other is numbers in a grid. But if you use our CSP framework, you suddenly see they have the exact same bones. For Sudoku, what are the variables? The empty squares. What's the domain? The numbers 1 through 9. And the constraints? You know these. No repeating numbers in any row, any column, or any of those little 3x3 boxes. See? 2 completely different puzzles, but they're built on the exact same structure.
So what's the big deal? Why go to all the trouble of framing problems like this? Well, because this isn't just about puzzles. This standard approach means we can build these really powerful general-purpose problem solvers that can take on some seriously complex, real-world stuff.
And I mean, these things are everywhere once you know what to look for. Trying to schedule all the classes at a university? That's a CSP. The variables are the classes, the domain is all the possible times and rooms, and the constraints are things like, hey, you can't have 2 classes in the same room at the same time, or this professor needs Fridays off. It's the same logic for scheduling flights, for planning delivery routes, for managing resources in a factory, even for designing the layout of computer chips.
Okay, so the big question is, how does putting a problem into this framework actually help a computer solve it? The magic isn't just in the organizing. It's in how those constraints,
The rules actively help the computer search for a solution and do it super efficiently.
There's this quote that just nails it. It says that a lot of problems that are intractable for a normal search can be solved fast when you frame them as a CSP. Intractable is just a fancy word for impossible to solve in a reasonable amount of time. Like, if a computer just tried every single possibility, it could literally take billions of years. But with a CSP, we can actually get an answer. To really get why, let's look at two different ways to solve this. You could use a brute force search, which is, well, it's the dumb way. It just tries every single possible combination of colors for the map. It'll get there eventually, but it's incredibly slow. A CSP solver, on the other hand, is smart. It uses something called constraint propagation. This means the rules aren't just used at the end to check if you're right. No, they're used all along the way to slash the number of options you even have to think about.
Let's jump back to our Australia map. Say we make our first move. We decide to color South Australia blue. Okay, decision made. Now, because South Australia touches 5 other regions, the moment we do that, our neighbor rule kicks in and spreads. It propagates. We know instantly that for those 5 neighbors, blue is no longer an option. It's off the table. We don't even have to waste time checking it later. We just eliminated it.
So what does that actually do for us? I mean, what's the impact? Well, with that one single choice, that one simple deduction, we just wiped out a massive number of bad combinations. For just those 5 neighbors, that one move reduces the work the computer has to do by, get this, 87%. That's not just a tiny tweak, that's a complete game changer. It's the difference between a problem being solvable or being totally impossible. That's the power of using constraints.
So, by breaking a problem down into variables, domains, and constraints, we give AI this really clean, structured way to think about complicated problems and find answers with amazing speed. But it all depends on having a fixed set of rules that don't change. Which leaves us with a pretty interesting question to chew on. What happens when the rules of the game themselves can change? How do you solve a problem like that? Well, that's a whole other story. Thanks for joining me on The Explainer.